Electrostatics 8. Electric field strength of continuous charge distributions. What are continuous charge distributions? Until now, we're talking about a point charge. But in practice, you don't get point charges or you don't get single electron or anything like that. In our day-to-day life situations, we'll get charges on metal surfaces, or that is conducting surfaces, or we'll be getting charges on the insulating objects. The basic unit of charge, which is charge of the electron, it's such a tiny one. You cannot simply see it with the naked eye, and you cannot touch and feel one single electron or few electrons. So practically we'll be dealing with electric charges which are formed on objects. Okay, so that will be the heading for today. Electric field strength due to continuous charge distributions. Okay, so that will be the heading. Look, these charge distributions can be of three types. One, a linear charge distribution. As the name suggests, this is charge along a line. I might show some positive charges lined up like this to form a line charge. Right now, I'm not saying whether this kind of a line charge is formed on a metal wire or simply some positive charges were stuck on a plastic strand, plastic sheet, plastic ribbon. That's not necessary to find out the electric field strength, because what matters is the electric charge which forms the field. So whether it is on a metal surface or on a non-metallic surface, non-metallic line, or a very thin wire on which this charge is supposedly formed, it doesn't matter to calculate field strength. So whether the charge is on a metal wire or a non-metallic wire, for example, it doesn't matter as far as the electric field strength calculations are concerned. To avoid some certain difficulties, what kind of difficulties? If it is a metal, charge will be there only on the surface. If it is non-metal, I can place it everywhere. So how to decide those things will be discussing separately. Why the charge should go to the surface, and how we'll write the electric field near that surface. Is there any difference? All that we'll see between what we do now and what we do later. So right now, just think of a charge distribution like this. This is what? A linear charge distribution. we can define one lambda here, one linear charge density. Lambda equals dq by dl, charge per unit length. This is called linear charge density. All right. And 2. A surface charge distribution. Actually, I might even drop distribution and say a surface charge, I can say. That you can think like this. Some charge is forming a surface. As I told you, where does it form right now will not be worried. You can think of some surface like that, imaginary one, and think that charge is somehow pasted, smeared on this. So our job is to find out the electric field and field strength of such surface charges. This is a linear charge, this is a surface charge. Here we define sigma, that is dq by dA, that is charge per unit area. This is charge per unit length. This was called linear charge density. This will be called surface charge density. Right? And next comes what? Third one. Can you not guess? Hello?
For a volume.
Volume charge. Isn't it? So a
Yes.
volume charge distribution. Or simply I'll write a volume charge. Okay? That may be, for example, a spherical volume I have. In that, I can think of many charges spread into that volume. In this connection, we define rho, that is dq by dv. Okay. What is this called? Volume charge density. All right. So our job is to find out the electric field strength of such continuous charge distributions. Can I turn my page?
Yes, sir.
Hope you're all writing along with me. Line charge, surface charge, volume charge. These are the practical things, right? They're very important in the electronic industry or electrical industry. Right, I'll continue. So we know how to find out the field strength of a Q. If there was a Q like this, a point charge, at a distance R, if it is a point, if the point charge is plus, we said E will be away from it. At that point, E is a vector. And its magnitude was found to be kq by r square. So similar idea we use here for a continuous charge distribution. For a continuous charge distribution, we'll find d first. But d is because of dq. D first means next we'll do something. I mean, I'll write first we'll find d due to dq. Then E due to the whole charge distribution is integral d, right? And
Yes.
d will be from this point charge formula k dq by r square r cap. Since I wrote vector here, I'm writing the vector here. And we already know dq equals lambda dl for linear charge, dq equals sigma dA for surface charge, like we did previously, we have written in the previous slide, and dq equals rho dV for volume charge. All right. So this is going to be the method for all values of the electric field strength we are going to find out for continuous charge distributions. Now, how to do it? We'll take few important standard cases and discuss them in details. So Trishul, tell me what is the general procedure? Already the rules are laid down here. Trishul.
Yes, sir.
So what is the general procedure we're going to follow?
First, we take a small L.
DQ. We take a DQ. DQ is
We take a small L.
small DQ. DQ is so small that
Charge.
it is like a point charge. Like a point charge. So point charge formula we use to find out DE. Then integrate the DE to get the total E, or the E due to the whole charge distribution. All right. Vaishnavi M.
Yes, sir.
Now, I'll actually show you one most important result. I'll go to the next slide. That is about E due to a finite line charge. What is a finite line charge? It has got known dimensions. This is a finite line charge, you can think. A finite line charge. It's not infinite. The ends are known to us here. You can think there to be positive charge. To be consistent, many times we put positive, and results will be slightly changing for a negative, only in terms of direction. You are given lambda, and you're also told that lambda is uniform. That means for every small dl, dq is same. You are asked to find out, for example, at a perpendicular, on the perpendicular bisector at a distance y, as to what is this E about. E is how much? Our job is this. The ends are known here. That's why it is called finite line charge. This is the perpendicular bisector. So you are going to get, or you should get, E in terms of what? Lambda and y. Of course, some constant might come, like epsilon 0, 4 pi, all that might come in. So these are the things given, just lambda and y. Or in the beginning, before lambda and y, we can also do something else. This angle is theta naught. This angle is theta naught. So E lambda and theta naught first. Later, in terms of y, lambda and y. Okay. So this is our job. I want you to write it, and I want to repeat the diagram in the next slide. Hope I can go to the next. Yes.
Why the perpendicular bisector?
Why not? Can you tell me why not? Look, we should be able to find out the value of E anywhere. All right.
Yes.
But mathematics will be a little not very tough, but you require more mathematics for that. So one of the cases is perpendicular bisector. Why not? The idea is to develop the techniques to find out E's, right?
Yes, sir. So we can take it anywhere, but for convenience, we're using perpendicular.
Not for convenience. That will be one particular case, right? So it is convenient to do the calculation,
yes.
not convenience for some other thing. In fact,
yes.
After this, we'll also find out at some other distance also, other place also, like somewhere here. Also we can do, we'll do actually. That's still a part of our syllabus. But when you ask such question, what was there on your mind?
So like it will be uniform from the perpendicular bisector on both the sides. So
it's not uniform. It's a kind of a symmetry.
yes. So like was that the reason why we're taking the perpendicular bisector?
No, we can do many things, no? There are many problems in physics. So why only that problem we can't say, no?
Yes.
Your question should have been, can we not directly find out at the general point if you wanted to ask?
Yes, sir. Like that.
At the general point also we can calculate. That's not a big deal. But this is an easier one. And then a little more difficulty, like that. The difficulty level keeps increasing. Okay.
Yes.
Right. Now, look at this. We'll take the line charge here. And as I told you, at this point somewhere, I should find out E. The ends are making angles theta naught, theta naught. First, I should get my formula in terms of theta naught and theta naught. I'll take this as my x equals to 0. And at a distance x, I'll take a small dx element here. Don't forget all this is positive charge, right? So a small dq element I've taken here. Dx is the length and charge is how much? Dq. So this dq is the charge I'm considering. Positive charge this is. So at this point, how will be my E? Away from dq, right?
Yes, sir.
away from dq. Slipping badly. At that point, remember, the electric field strength will be simply away from dq. Why? Because dq is a point charge. For a positive point charge, for a positive point charge, E will be away from the charge. We already know. But I need to get my variable here because he was asking in terms of the angles made by the ends. My variable is theta here. Theta becomes theta naught here, theta naught there later. Okay.
Yes, sir.
So if this is theta, this is going to be theta, right? So this d, whatever it is, has two components, d cos theta, d
Sin theta.
sin theta. So you can integrate both ex and ey. Or you want to make the calculations much simpler, you can consider one symmetrically opposite element which will have dE like that, right? This component gets cancelled. This is dE sin theta again, because if this is theta, this will be theta, right? dE cos theta once again. So you know that every two symmetrically opposite elements will cancel out their electric field strengths. This is to make the job somewhat shorter. Otherwise, you need not have to take one more element here. You can simply take x component to be there, y component to be there, and find out them. You might find the x component to be 0 after integration. Do you follow what I speak?
Yes,
So,
sir.
but now in advance, we can decide that the horizontal components cancel out. So only the vertical components remain. So the total E will be integral dE cos theta. Hope people understood it. The direction, this is magnitude way I'm doing. Direction is already known. It is, if it is positive charge, it is away from the positive charge as a whole. So, but what is dE? K dq by, let me say this is R. K dq by R square cos theta. I should get all my variables in terms of theta naught and theta naught. My result should be in theta naught and theta naught. Theta naught is the angles the edges make. This is my variable theta. So let me convert things into theta. Okay. From the figure I know this is E. I'll keep cos theta here, but convert everything else as much as possible into theta terms. Okay. Hello.
Yes.
So first of all, dq I want. dq equals lambda dx. Isn't it?
Yes.
That's how we define lambda equals dq by dl or something we told, right? Hello.
Yes, sir.
But I took x here, so simply lambda dx we wrote. All right. Now E becomes k lambda dx cos theta by r square. Nothing has come into thetas yet. Only k and lambda constants I could get from here. But I know here cos theta is equal to y by r. Okay. So
Yes.
r equals y by
Cos theta.
cos theta. Similarly, tan theta equals, tell me,
X by y.
x by y. Huh?
Yes, sir.
So y is the constant because I should get in terms of y. Let me find out derivative of tan theta with respect to derivative of x with respect to theta. That is y secant square theta
d theta
equals dx. Now all that let me substitute here. K lambda will come out. Dx is how much? Y secant square theta d theta. There's a cos theta here already by r square. Y square by cos square theta, which is secant square theta in the denominator itself. So this one will you get, isn't it?
Yes.
Look if there's any mistake in the calculation. So E equals K lambda by Y cos theta d theta. What are the limits now? If this is x equals 0, this side is minus theta naught, right? This is plus
theta naught.
Theta naught. All right. So I'll get
Yes.
K lambda by Y. What is integral cos theta d theta? Sin theta. Between, right? So what do I get? K lambda by Y sin theta naught minus sin theta naught, right?
Yes, 2 sin theta.
So 2k lambda sin theta naught by this particular formula is going to be very important formula as far as applications are concerned. But people can ask me any doubts they may have. So I want you to finish it and then tell me. Vaishnaviyam.
Yes, sir. Done, sir. Done, sir.
Done. Others, please.
Completed.
Now, this is in terms of theta naught and y, like we promised that we got. But now I'll get only in terms of y, which is not so difficult. But you need to tell me the formula. I'll go to the next slide. Okay.
Yes.
Now I'll just draw it again for reference. We have the charge, positive charge like this. To begin with, we found out E at a point which is on the perpendicular bisector. And we found that this E is which way? Straight like this. Isn't it? You have seen those components are adding up in that direction, right? This one. These were cancelling. So E will be away like that. Hope you agree.
Yes.
That one we calculated in terms of this and y. And how much is that? 2k lambda,
2k lambda
sine
90.
theta naught by y. K, is 1 by 4 pi epsilon 0. To just not to crowd the thing by writing all that, we are just writing it as k. Okay. Let me write what is sine theta naught. For that, I'll take this length to be 2a or 2l, doesn't matter. It will divide a and a.
Yes, sir.
So, in terms of total charge also I can write, in fact. So, total charge will be lambda into 2a. Isn't it? Charge density into total length of it. Hello?
Yes, sir.
Sine theta naught equals a by root of a square plus y square. Why are people so hesitant to accept it?
Yes, sir. Pythagoras theorem.
So E equals 2 into k 1 by 4 pi epsilon 0 lambda q by
2a.
2a into sine theta naught a by
under root of a square plus y.
A square plus y square under root, yes, into
1 by y.
Into 1 by this y is there still, right?
Yes, sir.
Yes, sir.
So what am I left with?
A gets cancelled.
So I'll get 1 by 4 pi epsilon 0 q divided by y into root of, this is in terms of q1 distances, where a is the half length of the line charge. So this is going to be very, very important for us to go for special cases and as well to apply it in various problems. For example, an immediate numerical I can give you. This is a square of side A. Okay. Somehow I've got plus line charge here and minus line charge here. Somehow, just don't worry. It is possible if I have non-conducting ribbons like that. Hello.
Yes, sir.
Minus here and plus this side. But both the charge densities are lambda each, plus lambda minus lambda there. At O, find the electric field strength. An immediate application. Come on, tell me how do you do that?
So, like, we consider the perpendicular bisectors.
Okay.
And then for the positive ones, it will be away from the bisector. For the
Okay.
negative sides, it will be towards the side only.
Right. So what she says is this. Say, let me consider this positive line.
Sir, the other is from the center.
So because of this, it is like this, right? E1.
Yes.
How much is that? This is y. Y will be how much? A by
E by 2.
2. And what is this angle?
45 degrees.
45 and 45. So E1 can I write straight away as using the formula old one?
2k by
2k lambda by A by 2 sine theta naught. Theta naught is 45. Sine 45. How much is this? 4k lambda by A 1 by root.
root 2.
Now it is easy. Due to minus charge,
It will be in the same direction.
same direction. Right? So in this direction, how much is my E?
2 into
8 k lambda by root 2a, right?
Yes.
Now, similar thing if you do, for this it is like this, and because this minus it is like this, right?
Yes, sir.
So it will
Same,
be 8k lambda by
root 2.
root 2a. So the net is like this from the middle. Huh?
Yes, sir. It will
Root
be
2 times 8k lambda by root 2a, right?
Yes, root 2 gets cancelled.
So 8k lambda by a. Do you follow? So an immediate application was shown.
Yes.
So may I continue for the next question, next slide.
Done, sir.
So I'll go to the next question, next slide.
Yes.
Now, some special cases let us consider for the same thing. Consider an infinite line charge. Infinite line charge. How does the formula change? Infinite line charge. What do you mean by that? We don't know the ends. Okay. Probably that line charge is now occupying my full screen. Do you understand what do I mean by this? I don't know the length of it. All this is a uniform line charge spread on a long, very long object like that, whatever it is. So in a distance y here, what will be theta naught? I should go join it at infinity, right?
90.
Yes, this will be pi by 2. Similarly, This side also is pi by 2. All right. So
Yes.
E will be 2k lambda by y sine 90. That is 2k lambda by y. If you'd like to write 1 by 4 pi epsilon 0 also, you can write. All right.
Yes.
Hope people understood why these angles are pi by 2. Huh? Because these ends we don't see. This is here, this is there. Hello.
Yes. Sir.
Yes, sir.
Right. I'll go to the next one. Can I continue?
Yes, sir.
Yes, sir.
Next, we have at the end of a infinite line charge, in the sense people call it semi-finite or semi-infinite. One side I know, but the other side is infinite. Like this. At this one, I want to find out. Tell me. This
So
angle.
one side theta
Huh?
not, one side 90.
Tell me.
No, sir. Here we'll have only one side, so that will be 90.
So this is 90. This will be 0.
Yes.
Is it 0 or not? This side angle.
Yes.
So what will I get?
So in the integration formula, sine theta from minus theta to theta. Sorry.
Okay, tell me. Look into that and tell me. Actually, if I give you straight away, it doesn't look nice. You'll just take it. No, there's no thinking happening, so it will conveniently go away. Like the ideas, you need to marry them, then they'll stay with you. Ideas you need to love, then only they'll stay with you. Go somewhere in a crowd, introduce yourself to somebody and come away. You won't even remember whom you met, or you will just the face or some name you remember, but you cannot do anything with them later. So how do you own up the ideas? Now there is already something given there. Now can I get something out of this using the old ones? Tell me.
So will it be k lambda by y?
A lambda by y. Just tell me, just speak out. I'll write for you, and if there is a correction, we'll make it.
Or in the
Sir,
derivation?
limits will it be 0 to pi by 2?
Limit 0 to
Pi by 2.
pi by 2. So tell me that final formula we had, E equals, tell me, look into your notes and tell me. K lambda by y,
Yes,
Theta
sine
from
theta
integral
naught.
cos theta d theta we had, or
yes.
2 was there, I don't know.
Yes,
Just
sir.
2
was
was
2 here?
no, sir.
No, this was the idea. So what you're saying is now, so this side it is 0 angle, this side it is 90. So 0 to pi by 2 you want me to put, I'll put it. So k lambda by y, what is integral cos theta?
Sine theta.
Sine theta between 0 to pi by 2, which is k lambda by y, sine 90 minus sine 0.
Plus sine 0.
No problem, actually. Huh? But
Yes.
there's an issue. This will be only the y component, children. There will be an x component also here. Because we took somewhere in the middle there, the components that side, this side got cancelled. Hello.
Yes, sir. Previously, X components got cancelled.
Yeah, now x components are there. They cannot cancel because there's no other side here to cancel out the x component, right? So this was
Yes, sir.
this all what we did for the y component, children. Do you agree? Refer
Yes,
back
sir.
to the notes. So this is okay, but this is only the y component.
For
So yeah.
y component.
So this is y component ey. This is k lambda by y. There will be an x component, of course, it will be like this. It should be like this. It cannot be like that because E cannot be that way. For this all positive charge, E should be away from it, right? Huh?
Yes, sir.
So it will be like that. So this is okay. K lambda by V is okay. How much is EX?
So instead of cos theta, and we should do sine theta.
Okay, let me try. EX equals K lambda by Y. She says you get sine theta here. Are you sure about it? Huh? 0 to 90 again. So K lambda by Y minus cos
theta
to 0 to pi by 2. So what do I get, Sriya? Minus cos 90.
0.
Minus cos 0. Plus 1. Isn't it?
Yes, sir.
So it is K lambda by Y again.
So we'll get root 2 K lambda by
Root 2. But is this okay, children? This is okay. Actually, refer back to the old derivation, you will understand it. Huh?
Yes, sir.
So this is correct. But I can also tell you something else if you are ready to follow.
Yes, sir.
I have put something here. Half. It looks as if I have removed half from the old one, isn't it?
Yes, sir.
Yes, sir.
It looks like I removed half from the old one. Do you agree?
Yes, sir.
Yes.
So if I add half more this side, E will be this way, isn't it? Complete E.
Yes, sir. X gets cancelled.
I removed it, so it went like this. Hello.
Yes, sir.
So without doing this, I can guess that the other component also should be K lambda by Y if I use that idea. Tell me. I've given you a clue here. If half more was there, there would be E like that. In other words, for the other half, it should be like that, isn't it? Hello?
Yes, sir. It will repel.
For the other half, if I think there is one more half this side, it will be like that. Sum of these two should be equal to this. And that was how much? 2K lambda by Y. This is the resultant of two equal things like that with an angle of 90.
Yes.
So should it be not root 2 K lambda by Y, and this is root 2 K lambda by Y? Hello?
Yes, sir. Like the vector sum will
Yes.
be.
Vector sum will be this, right? Agreed?
Yes.
So if it
Yes,
is
sir.
root 2 K lambda by Y like that, so if it is K lambda by Y for our half one, can the other not be K lambda by Y this way?
Yes, sir.
I
Naturally.
don't know whether people understood only.
Yes, sir.
Understood.
Understood.
We take the x direction ones and take x and y.
I thought of having half more, and I said, because the total is this, because the angle is 90, each of them should be root 2k lambda by root 2k lambda by this one. Do you follow? Hello?
Yes.
This one is root 2k lambda by, I guessed. And if this is root 2k lambda by y, this is k lambda by y, this should be k lambda by y. Do you follow?
Yes.
Yes, the component.
There all be 90-degree angles.
Huh? Hello?
Yes, sir. If we take the x components, there will be 90 degrees between x and y component.
I really don't know how many of you followed it. So can I continue now? Remember, if you remembered, if you understood this, you remember it without any special effort. And you'll be in a position to apply it also later. See, I've already shown you the applications, try to understand. And this is what you call, this is generally people call it semi-finite or semi-infinite, anything, because one side is infinity, other side is finite here. So from the old one only I got this. Agreed?
Yes, sir.
Yes.
Come on, now. So considered an infinitely long line charge, considered a finite on one side, infinite on the other side. Now, I'll consider a special case like this. Tell me this one. Like I'll draw the thing again, but this side I'll change my direction because this is the breadth side I have here. So how much was E here for a finite one? This is theta naught, this is theta naught, and this is y, this is 2a. Okay. Now in terms of a and y, what was E? Not in terms of theta naught, I'll remove that. So in terms of lambda, all these things. In terms of, sorry, that Q and this Q, A, Y, what is E here?
1 by 4 pi epsilon. Q by y under root of a square plus y square.
Now consider y to be larger than a. Could you tell me what will it become?
Y q by y square will come.
General cases, the limiting conditions become special cases. General cases in the limiting conditions become special cases. So we can be sure that whatever we did is right, because if y is very large, this is like a point charge. The dimension of this doesn't matter for a very long distance. But remember, y is not infinity. Huh? So you got a point charge formula, right?
Yes, sir.
Now, I'll give you a little homework. In fact, if you understood what I've told you, it's not so difficult. But I'll just show you. Because in the very beginning, Sri, I was asking a question, why only on the perpendicular bisector? Now, homework for you. I have a finite length of a line charge. Okay. But now, I don't go for perpendicular bisector. This one. This edge is making theta 1. This edge is making theta 2. At this point, how much is E? Have you understood what the question is demanding from you?
Yes.
Now we can say
Yes.
X and Y components don't cancel. And you're already having X and Y components made ready for you there. So you can get X and Y by integrating between proper limits. Do you follow? After which, if you want the magnitude of that, you can write E equals EX square plus EY square under root. Here, this is lambda. In terms of lambda, that's enough. Lambda y, theta 1, theta 2. If you do, that's enough. Have you followed my question here? You'll find out.
Yes, sir.
Ex. The mass is there for you already there in the beginning itself. And Ey. Here, Ex's won't cancel because non-symmetry, right? Hello.
Yes.
Yes, sir.
So this much, I mean, almost everything is known. You can make almost a guess of what is going to happen. But anyway, I'll give you time until tomorrow to come ready with the derivation. We did only one, but it's worth doing because it is the most important thing. Remember, at the lower level exams, questions will be based on only the formulas, but at the higher level exam, this will come as one component of the problem, not everything. There'll be too many components in the same problem. There will be too many ideas in the same problem. So we need to really feel very, very comfortable and internalize the whole idea by looking at it again and writing for yourself on a paper and trying to derive it, trying to think about it. Okay. So this tomorrow I'll ask you, but right now I'll be closing the session.
Sir, won't we need the length of the line?
You don't require. In terms of theta 1, theta 2, y only you will get. Okay.
Okay, sir.
Thank you, children.